Hey guys, I quickly wanted to go over some different bond types because I know there's a bit of confusion in recitation this week. So basically we've got these two main types of bonds, intramolecular and intermolecular. And the main difference between them is, as you can see, intramolecular bonds are going to be between two atoms within one molecule. So as you can see here, they're going to be that oxygen-hydrogen bond within the water molecule, whereas intermolecular bonds are between two atoms of two different molecules. So there'll be that hydrogen bond between the two separate water molecules. Now, intramolecular bonds are going to be a lot stronger than intermolecular bonds, and if you think about it, that makes sense, right? Because it's a lot easier to break apart two different molecules than it is to break apart the atoms within one molecule. So, looking at the three main types of intramolecular bonds that we're going to be thinking about in Orgo, and these are all considered fairly strong bonds where the strength might bleed into each other a little bit, so we don't want to make a strict separation, but these are kind of ranked by how much the electrons are shared between the atoms. So in ionic bonds, this is an electrostatic force where the protons of one atom are attracted to the electrons of another. What that really means is that the electronegativity difference is going to be great. This is ones where the electronegativity difference is above 2. So we get into that sodium chloride bonds where we see one positive and one negative ion, like you can see here, where sodium is positive and chlorine is negative. So that really means that there's a full separation of charges there, where one atom is completely taking all of the electrons. Next, we get into polar covalent, and this is where electrons are not shared equally as well as ionic bonds, but there is a little bit more of that sharing going on. That's why they're called covalent. This is going to be electronegativity difference greater than 0.5, less than about 1.7. And so electrons here spend most of their time around the more electronegative atom. So here, for instance, in the oxygen, it's going to carry a partially negative charge, whereas the hydrogens are going to be more partially positive because the oxygen has more of that greater electron density. So these are going to be bonds like carbon-oxygen, oxygen-hydrogen, nitrogen-hydrogen. And last but not least, we get into nonpolar covalent bonds. And this is where electrons are shared equally, or mostly equally. And so the electronegativity difference here is going to be just less than 0.5. So here we get into all the bonds that are like oxygen-oxygen, carbon-carbon, which those are for sure nonpolar because electronegativity difference there is 0. But we've also got carbon-hydrogen and carbon-sulfur, that type, where it's just slight electronegativity difference. So, moving on to intermolecular bonds, and just remember that all of the intramolecular bonds are going to be stronger than the intermolecular bonds. But here we have, and this is strongest to weakest, hydrogen bonds, which is when a covalently bound hydrogen, so for instance that oxygen-hydrogen bond we were talking about, where that hydrogen can interact with an electronegative atom. So here these atoms we're talking about are going to be nitrogen, oxygen, fluorine. And the thing about that atom though is it has to have a free lone pair. So for instance here, that oxygen on the water molecule has 2 free lone pairs. So a lone pair there can interact with a hydrogen of another water molecule. And this keeps all of those water molecules really bound tightly together, and it makes sense on why water has that property of cohesion. So here, this is ranked based on strength. And so basically, the more electronegative the atom is, the stronger the hydrogen bond it's going to have. So hydrogen fluorine, because fluorine's the most electronegative element, that's going to be stronger than our hydrogen oxygen and hydrogen nitrogen bonds. So next on the strength list, we've got dipole-dipole interactions. So these are, again, electrostatic forces between two different polar molecules. And this one, it's weaker than a hydrogen bond, but it's not as weak as London dispersion forces. And these are going to be our weakest type of interaction, where they're forming temporary dipoles with another molecule. So this really bleeds into boiling point a lot because the stronger the bond type is, the stronger the intermolecular bond type is, the higher the boiling point is going to be. And this makes sense because the more tightly bound it is to the other molecules, the harder it's going to be to break those bonds. So that means that a molecule that has all hydrogen bonding going on and dipole-dipole interactions, that's going to have a higher boiling point than a molecule that maybe just has London dispersion forces bonding them together. And that's also why a molecule that has more hydrogen bonding and is polar is going to travel less on the TLC plate than a molecule that is nonpolar and just uses London dispersion forces, which we'll get into in Orgo Lab. So go ahead and take a screenshot again as a cheat sheet if you want, and thank you guys so much for listening.